So Monday night, you heard me talk a little bit about the early concept of the 9-day study, according to Tom. I thought it was 2 weeks, that we put an initial concept together and went down to talk to NASA about it. Today, I'm going to take you from that time to the launch. And some of this will remind you of the systems aboard. So to many of you, you'll see things that you've seen before. And I'll talk a little bit about, as we go along, some of the oh my gods that we had, the near-death experiences as Micah was talking about the other day. So I'm going to talk about the story of the development, about how the mission concept was developed, how was the team organized, how did that spacecraft concept evolve? And it evolved from that initial thinking we had in 2000. Then what were the technical and schedule challenges? I'll talk a little bit about those. We'll talk about how the mission team's strategies managed the long duration mission were accomplished. Who made it happen? And that's the most important thing that I could talk about, is the team, the wonderful team that actually made this come from an idea to reality. And then what was the key to success? So I'm going to start with the last thing first, and that is the passion and the hard work of the team, starting with Alan and the team at Southwest, the team here at APL, that all came together to make this a success. I often say it's, my general answer is work to be fortunate. And I think that's the story of the New Horizons mission. So I want to take you back to something most of you already know. This is, your eyes may glaze over with this particular chart, but I want to take you back to what we were thinking in 2000 and 2001. From that early concept study, we understood, we're going to launch from the Earth, we're going to fly by Jupiter, and we're going to go out to Pluto. And this is the time scale that we eventually had as we finally resolved this. I could talk about iterations in between, but I don't want to bore you to death. So from this, we understood certain things. One was, out there at Pluto, you've got to have a radioisotope thermoelectric generator. You've got to have certain mass limitations for the spacecraft. You've got to have a launch vehicle that'll get you out there. So those were some of the constraints that we had as we thought about the mission itself. So the first thing, of course, that happened as we came up with these ideas, these concepts, as the two components of the team, the people like Alan at Southwest at APL, it was in December of 2000 that Tom talked about, where here at APL, we were talking about who would we join up with. We understood that we did not have the scientific expertise to drive the mission. So we were looking for alternatives, and we settled easily on Alan. So that it was that settling in over the Christmas holidays that I think Tom Comedius reached out to Alan, and we made the agreement that we were going to join together to put in a proposal. So writing the proposal, what were the strategies? First, team leadership. So that was the science part of the mission led by Alan, and then the mission management institution at APL, giving our background, as you've heard, about the expertise we brought, and the understanding and the belief that it could be done that NEAR brought to us, and NASA then believed that we could actually achieve that kind of a mission. We ended up with still a simple architecture. That was key, I think, to everything that followed. We ended up with an architecture. We used the Ulysses spacecraft as the model, as you heard the other night. And then we were very careful about drawing on past history of components. And there's been a history of that here at APL. The near mission succeeded so well because there was a previous mission called MSX. MSX had a lot of electronics. It was built and supported by the Missile Defense Agency. And NEAR drew a lot upon the electronics associated with that mission to make NEAR come together so quickly. Our original proposal was to use the contour electronics to, again, be able to make copies in a different configuration mechanically, but a lot of the electronics would start with that. And then we were disciplined about the instrumentation we were going to use. The resounding theme early on was, we're not, and this came from Alan, we're not going to put a Christmas tree on this mission. And we were very careful to choose the instrumentation. We were focused on what the science team said the science was required. And we focused on that. And we ended up with choosing only one new technology. This was not a technology mission. This was a science mission, and that was a key focus for us. But we did choose one, a digital receiver. That technology was mature enough that we were very confident it would work. Turned out that ended up being a key decision along the line. And I'll tell you about that in a minute. And our initial goals were to have a very short timescale schedule. We were going to use known technologies, and we're going to keep the schedule short. Keeping the schedule short keeps the cost down. We almost achieved that, but we had some issues that arose that made it not as short as we wanted, but still short in comparison to other missions. I just want to show this. This is the organization chart, and the thing I want you to, you're obviously not going to read all this, but the thing that I wanted to emphasize here is how Southwest and APL integrated the team. The blue boxes are parts of the team that were led by Southwest Research. The brown orange blocks were APL. APL focused on the spacecraft. Southwest led the instrument development, although there were instruments developed at APL, as well as one of the instruments at Ball that was a contract at Southwest. But this team came together as a team. It wasn't, I go talk to my contract agent. It was, the small team of us that were the leadership would meet once a week, and we really worked together to make this happen. So there were some changes along the line as we went. So in January the 15th, 2002, we just had a contract. So I and a few other members of the team went down to NASA headquarters. We walked into a meeting, and they congratulated us for winning. And they said, oh, we're going to make some changes. We don't have enough money to get you on the schedule you had proposed, which was a launch in December of 2004. You're going to slip, and you're going to end up with a launch in 2006. And oh yes, you had proposed to use the already existing RTG. We're going to give you a new and better RTG. They had the parts for an RTG unfueled, so they were going to assemble that and give us that new RTG, which give us more power. And so we had those things. And then the other thing that was happening in this time, there were continued concerns about the reliability and the resilience of missions, and that affected some of the systems on board the spacecraft that added complexity. So we did a number of things. We made trades to use the extra power we were going to get. So we made the antenna smaller, and we used that mass for other things. One of the big things, we could add more propellant to the mission. That really served us well when we wanted to go into the Kuiper Belt. We continued to limit the technologies to just one, so that stayed the same. We added deeper redundancy. The autonomy system got more complex. And we still had to aggressively deal with the schedule. And then we began the structure development fabrication just as early as we possibly could. We let the contracts right after PDR. We couldn't fund them completely, but we got them started. So that helped us with schedule. We ended up with, these are the instruments that you all know very well. And the thing that is very interesting about that, again, with the focus, so all these instruments combined weigh 32 kilograms. People remind me that the imaging system on Cassini weighs a lot more. So we were able to keep the mass down of these instruments. So that was very important. Our mass limitation was 477 kilograms. That was the mass we had to get to we could launch and make the schedule and get to Pluto by 2015. And so this is the way the instruments were placed on the spacecraft. Again, you recognize all of this, I'm sure. But again, that basic concept we had back in 2000, using the Ulysses spacecraft as the model, is what we ended up with. Again, this is an eye chart, but there's two things about it. It's green. It's green because still in the year 2025, all the systems still work. All the concerns about possible failures never happened. There's a few things we never got to check out because we didn't need them. The other thing about it is the redundancy. You'll see 2 integrated electronics modules. So we had redundant flight computers, flight guidance and control computers. We ended up with a 240 gigabit solid state recorder on board, one on each of the IEMs. These are the systems that allowed us to operate and collect a lot more data. In our original proposal, we had proposed to bring down only 7 gigabits of data. I think you'll remember that. We ended up having over 240 gigabits. And luckily, we had that memory because we had a very exciting object to look at. It wasn't, as someone was saying, worried about it being a ball, a bowling ball kind of look to the planet. And then we ended up then the other thing was this careful balancing of requirements. We were very careful to focus on the science requirements, only what they required in the spacecraft. And we ended up being able to build a spacecraft that's about the size of a concert grand piano. I often say with the salad bowl on top for the antenna. And you see here a technician putting the final touches on the thermal blankets. This is at Kennedy Space Center. One of the concerns that I had early on was how are we going to keep the spacecraft warm? Well, Doug Miho, our thermal engineer, said, not a problem at all. We'll just wrap it very carefully with thermal blankets and it'll look like a thermos bottle. And it's still operating within very comfortable temperatures today. And one of the things we have done as part of the design to begin with is that we operate the spacecraft most of its life spinning. So we had this long duration between launch and Pluto, and we didn't want to operate the systems. We have a propulsion system that allowed us to orient the spacecraft, do trajectory corrections, but we didn't want to use it very much. So we could spin the spacecraft at 5 RPM, point the antenna toward the Earth, and go away from it and expect it to go back and talk to it again when we came out of what we called hibernation, where we had this low energy mode. We did not use the systems for months at a time. And that allows us to reduce the amount of effort we take to keep the system operating. Also, the ground system was very important. So the ground system itself was a fairly complex system. And there are 2 or 3 things that I wanted to bring up. The Mach itself, which uses the DSN to talk to the spacecraft. It also interacts with the navigation system, mission design, all these other elements with the science team that provides the control, the guidance for what we're going to do with the spacecraft that the mission operations team turns into command loads. We also have simulators. There's actually 2 of them that we can then fly, we can operate and test out every command load on those simulators. Those simulators became very, very important as we got into the mission and the complexity of the mission as we flew by Pluto. So I've kind of given you, this is where we got to. Now we want to talk about what the challenges were. And I've chosen 4 risks to talk a little bit about. I talked about one near-death experience with the hurricane. I don't have that one on here because it happened too fast for it to show up as a risk. But the first one is the NEPA launch approval. And I'll talk more about why that was an issue in a minute. But the principal thing was that the previous mission had taken 7 years to get launch approval, and we only had 4. We understood that there would be a lot of complexity to that. So in our proposal, that was a red risk. That was a risk that we thought it would be mission ending. You know, if we could not get launch approval, we couldn't launch. Others came into this area, many of them very late in the mission. I'll talk about those. The autonomy was a concern to the very end because it became much more complex. The power margin, we had this new and wonderful RTG with new fuel that created a problem. And then we had a launch vehicle near-death experience in the fall of 2005. So autonomy. So this is a chart that we've used many times to talk various modes that a spacecraft can operate in. You know, 3-axis mode, active spin, what we call passive spin. There are various operational modes. And then if something fails on the spacecraft, we can switch to the redundant system. Anytime we would do that, except for one case, you would end up going into a phone home. The spacecraft would be told to spin up, if it was at 3-axis, spin up to 5 RPM, point to the Earth, and send out what we call a red beacon. The one case, and there's 2 options of that. One is if we assume the spacecraft knows where the Earth is, so it can point. But should that fail as well, we have a sun sensor on board. So if all else fails, the spacecraft is told, go find the sun, go point to the sun. And we know that the Earth will pass through that line between the spacecraft and the sun at some point during its orbit. So we would be able to communicate with the spacecraft. The other one that we don't operate in that mode is the 3-axis encounter mode. In that case, we don't want it to phone home. We want it to fix itself and continue making the observations. It will take greater risk, but the greatest risk is not to continue the observations during the encounter. This added a huge amount of complexity to the system. There's like over 160 rules that the spacecraft autonomy system, and that was a greater, more complex system than we originally proposed. And the real challenge is to test it. There are probably 1 trillion potential paths in the system. You can't test all of them. So it was important for the autonomy team to figure out which ones were important to test and get it done. They finally signed off in December of 2005 that they were ready to launch the spacecraft. We did actually agree that there were certain modes we wouldn't operate on the spacecraft until after we were launched, because they wanted to do some more testing. But all the testing showed that the system really worked. So launch approval was a big deal. And this chart gives you some sense because there are so many organizations that have to play in this. not only the project, but the launch vehicle, NASA headquarters, the Department of Energy, all were involved in getting launch approval. And you had to get all these groups working together to get all of this done on time. Luckily, we had a team across this board. Lyle Rutgers at DOE led the launch approval activity at DOE. We had expertise with Yale Cheng here at the laboratory, so we understood the kind of problems we're going to have. We had many, many meetings. Kurt Lindstrom, as the program executive downtown, really guided the activity from the NASA point of view. But all these organizations were involved in getting a very complex set of systems. One of the issues, for instance, we had a third stage which was had solid rocket propellant in it. There had been a failure of a Delta mission some years before in which it failed on the launch pad. The third stage came down as a burning rocket propellant on the ground. There was grave concern that if such an accident occurred for New Horizons, that the propellant could burn and penetrate into the RTG and allow the plutonium to be exposed, and we'd have a radiation hazard, health hazard. We ended up running a test at China Lake where we simulated. There was a big argument among the safety team that the solving that there was 2 charges on the third stage. So if something happened, we would blow up the third stage so the propellant wouldn't be a large amount of material in one place. Then the concern was, well, when you blew it up, some of that would penetrate the RTG and expose the plutonium. So we ended up running a test at at China Lake, simulating all of that to demonstrate that explosion of the third stage would not create a problem to the RTG. So those are some of the things that had to be done to get launch approval. The other one was that was a near-death experience was in 2004, the Department of Energy came to us and said, we're not going to be able to make enough propellant, enough fuel for your RTG to meet your launch date. We're going to have to slip. The problem was that at Los Alamos, who actually converted the raw plutonium to the pellets that go into the RTG, it had a couple of, one was a safety issue, another one was a security issue that shut down the production. And each time it shut down, it delayed the production of plutonium. So by the summer of 2004, DOE was convinced they couldn't meet our requirement. That's that line you see at the top. Let's see now. If I use this. So this is the original RTG power. So it goes down about an 87-year half-life. And so we were supposed to get on the order of 230 some watts when we got to Pluto. And they weren't going to be able to meet that. Luckily, Chris Hersman, our spacecraft systems engineer, asked, how much can you provide? We agreed within about 2 weeks that if they could supply 180 watts, these are the operating modes we would operate at space at Pluto. And the reason we could do these, one of them was that digital receiver I talked about. That reduced the amount of power that we always had to keep on in the command receiver by 15 watts. So that would have put this number up here. Okay, so that technology saved the day for this. DOE came back and said, we can meet that requirement. So we ended up getting actually better than that. They ended up providing 200 watts as we flew by Pluto. So we were in good shape, but it was because we could agree upon operating at a lower power than they originally promised, even though we used some of that power to reduce the spacecraft mass. And so here we are This is November of 2005. You see the flight RTG. This is the first time it was assembled with the spacecraft. And that's a very touchy operation. The the RTG is running at about 100 degrees centigrade, maybe a little lower in air, and is putting off alpha particles. So making this kind of adjustment is a very careful operation. The other near-death experience was with the third stage, the first stage of the Atlas V. This is a blow-up of the Atlas V. You see the spacecraft up there. It looks like a hood ornament on the whole arrangement of 200 foot. In 2005, in September, the Lockheed Martin people were running a test on the first stage. They're trying to test the maximum stress it was designed to operate in. It failed dramatically on the test. And there, everybody was worried that we would have a failure on the launch pad of that first stage. And it came close to canceling the mission again. It took a meeting downtown with a NASA administrator who made the decision, and I think it was about the 11th of January, that we were going to fly. Alan was at that meeting. If you want to know more about it, you can talk to Alan. So who made this happen? Several thousand people. And I love this picture on the right. This is a group of people that were doing the final spin balance of the stack before it was being put on the launch vehicle. You see the third stage this is a solid propellant third stage that sets it, and we sit on top of that. And that was the final piece that gets us on the way. 50 organizations and more, and several thousand people actually made this happen. It was quite a team. So we went from a proposal in 2001. We were given a contract in January 2002. And 4 years later, we were on the launch pad. Went from that concept to the reality you see in that lower picture. This is part of that dedicated team. You see them in two times, one in 2004 and then in 2015, about the time of the flyby. These are the people that made this happen. They're part of the team that made it happen. There were many others. And so we had the fastest launch ever at 36,000 miles on January the 19th. So at that time, Alan, myself, and Dave Cooch were in the Launch Control Center at Kennedy Space Center. And I remember this quite well. So counted down, the launch got off. Alan, so we were told not to go outside the building because if some of the worst case launch accidents could affect the building itself in the environment. But Alan wanted to see the launch with his own eyes. So he headed for a door and got out to see it. I waited inside. There were two things that I wanted to hear. One was that after 27 seconds, the rocket would be out over the ocean. At that point, an accident would reduce any risk of contamination by another order or two of magnitude from the already low number. So we were way much safer at that point. And then about 40 minutes later, I heard from the mission operations team. They had made contact with the spacecraft. All the systems were operating, and we were clearly on our way to Pluto. So one epilogue to that. We had set aside 90 meters per second of our 300 plus meters per second propellant capability to make adjustments to any launch errors that we got. After we quickly looked at this, and you may hear more about this from the navigation team, we got down to needing only 28 meters per second of that to make corrections. The launch people had done a great job of getting us on our way. And that served us extremely well when we went out further into the Kuiper Belt. So that was the story of the great challenge of this mission and the great team that made it happen. Thank you.
Open for questions.
There's a set of classic questions that ends with, what job other than your own would you like to have, and what one would you least want to have? And the first thing that would jump into my head was always getting through New Horizons launch approval. So thank you, thank you, thank you.
Did I hear correctly? Did you have a 2004 launch target date?
Yeah, it was December of 2004.
What year?
Okay. And that was based on NEAR. NEAR was done in 3 years.
Could you have actually made that launch date?
So that our proposal had a December of 2004 launch date. We also agreed that we were going to use so I'll come back to the story about the RTG. We had proposed to use the already existing built RTG. So that was not going to be a schedule issue. And we were going to more heavily rely upon the contour system architecture. So all those things, but we also needed to ramp up very quickly in funding. That was one of the problems that couldn't happen. And of course, the RTG problem, what really was driving that, during the end of the Cold War, the agreements between ourselves and the Russians, we bought a lot of plutonium from the Russians. The requirement was it had to be only used for civilian uses. The existing RTG did not have that constraint. So DOE wanted to reserve the plutonium in the existing RTG, and therefore they would use the Russian plutonium that had to turn into usable fuel for us. And that's why they chose to give us the bigger and better RTG that nearly killed us.
Technically, could you have made that date?
What's that?
Technologically, could you have made that date?
I'm sorry. Yeah.
Yes or no?
It would have been a challenge.
Challenge to that.
But we made it. We did it for NEAR. I think we did have some challenges, particularly on some of the instrumentation, and many of those challenges were only partially technical. One of the big challenges, and especially with one of the instruments, was that the team was building that. The people kept getting pulled off to do other work. And that became a big issue between Alan and I and that particular contractor to get it done. They did get it done in time. That would have been a real challenge to get December 2004 launch. Yes.
Hi. For those online, this is Kelsey Singer from Southwest Research Institute. Glenn, I have two questions, so I'll just ask the first one and let you answer and then go to the second one. Do you think it's easier or harder now to do things on such a short timeline?
I think what happens is that after we've done certain missions, then to go to the next step, it gets more complex. And therefore it takes longer. And the budget problems become actually a big constraint. And Dragonfly as a case study of that is how it's been drug out, mainly because NASA kept coming back and said, you can't get the money we promised you. This is when the community gets together and they find a new way of doing something. This is the kind of challenge that I think we're going to have, is that we're going to have to think anew and find a slightly different path for the kind of science we want to return. I mean, last decadal, we were talking about missions to places like Uranus with an orbiter, and it takes 3 RTGs, you know, all this kind of stuff. And they're great missions. Okay, so can you get the political will that we were talking about to do those kind of missions? That's what happened, I think, in the 90s, is there wasn't the political will to do enough of this, and that we found a slightly different way. It reduced the cost because we're more focused. So it's going to be the challenges of the future to figure out what those focus missions look like if we're going to get them with any kind of rapidity.
Yeah, that's a really great answer. Also, I just wanted to say that this was an awesome overview, and I hope I can get the slides from you at some point.
Okay.
My next question was about, can you say a little bit more about what you think are what helped with New Horizons and what the best practices are for managing, you said aggressively managing risks?
Yeah, so I'll tell you a funny story. So I put up a risk chart that looked a bit like the one you just saw at one of the science team meetings. And someone came up to me and says, "You're not going to show that to NASA, are you?" And I said, "Yeah, because that's where I thought we were." So I said, you know, the launch approval was a red risk at the beginning. In 2016, I was on a panel that Ed Weiler chaired, and this was a group of people that were talking about various missions that was for the people that were just about to take on a new discovery program, or maybe it was New Frontiers mission, I can't remember. And I basically put up a chart like that. And I mentioned that I had that as a red risk at the beginning. And Weiler shot back, "If you hadn't have put it as a red risk, I would not have chosen you because you clearly did not understand the problem."
Interesting.
So first thing you need to do is be honest with yourself. Okay. And the other thing is to be very careful about your team. Do you have the right mix of people? And then you need to listen carefully to them to be sure if they've got a problem, you can figure out how to solve it. And those are the keys to success. Having a great team, that's the first fundamental thing. And then allowing them to get the job done and being sure they understand what the goals are clearly, and help them be sure that barriers don't get in their way.
Yeah, those are really great pieces of advice. Thank you.
Time for one more. Elliot Young, Southwest. Glenn, I wonder, you talked about finding a new way to do things with, you know, smaller and cheaper and more focused missions. But I wonder if you have any perspective on simplex missions and why they seem to be in such trouble and, you know, in perpetual hold.
I don't know if I've got an answer to that. I mean, it's this right balance. You have to have the will to make them happen. So we had proposed a mission that was, you know, we said under $500 million. Our final cost as we flew by Pluto, the funding we got through 2016 was $720 million, but that included $200 million for the launch vehicle. I think the keys are to find a mission that will have enough clout that you can keep it going. So when it runs into problems, there's the political will to keep it going. That's what happened with New Horizons. And so I think it's that combination. And then you got to be focused, but if you oversell something, you're going to be, that's what happened with many of the other Pluto missions. They oversold it and got very narrow in the end. No one believed them. It's that combination, that balance.
Yeah, so I've asked this to Alan and I've asked this to Will, and it was, what is the one thing you could have if you could have added anything to the spacecraft, what is the one thing? Alan said a larger antenna. Will said reaction wheels. What is the one thing you would have added?
And I understand why they would say both of those things. What would I have changed? Yeah, I would think getting more data down would probably be the thing I would go for. Reaction wheels, I would have loved, but we were always concerned, would they operate for that long a period of time? That's why we used propulsion system to do all the attitude control. That was the choice we made. Okay.